Well, it's 10:30. So let me first get the bad stuff out of the way. A pack of stuff I bring to class every day, papers and everything. I don't know where my head was this morning, but I forgot it. The most important thing, I think, is if I have some homework of yours that I should be passing back, I don't have it here. Although if it was the last assignment, I probably didn't get it back from my grader anyway. But Monday being the exam, if you feel like you would really like to see your homework, please just drop me an email and I will scan it and send it to you over the weekend. So that's first item. Second item, midterm exam on Monday. If anyone has questions on homework problem or on anything on that handout, you could ask me now, or you might have time at the end of the class. I'm going to try and be in my office from around 2 o'clock on, so till maybe 4 if you want to come by. Okay. Though I do not have my notes, I am prepared, so why don't we go forward. We're going to finish up on triangle trigonometry. We're not going to be finished with it until the end of the year, but there was a detail that has come up, but I want to formalize. If I have a right triangle with some angle theta, and I have my hypotenuse, my opposite side, and my adjacent side, we define some trigonometric functions in terms of this. We said the sine of theta is the opposite over the hypotenuse, cosine of theta, the adjacent over the hypotenuse, and we'll work more with the tangent at some point. That's the opposite over the adjacent. Well, this being a right triangle, this angle here is a complementary angle. So we know that this angle is 90 degrees minus theta. And if, you know, I'm so used to looking at it this way that it's actually hard, but in my head, I'm going to tilt this over so that this is now the angle I'm looking at. And now the sine of 90 degrees minus theta is now the side opposite, which is now what we're calling the adjacent over the hypotenuse. The cosine of 90 degrees minus theta, okay, that's this side, that side which is the adjacent to this angle that we're calling the opposite over the hypotenuse. And the tangent, well, tangent is the opposite over the adjacent, but that's A over O. Well, you'd rather sit up front, you can. It's not a problem. Well, as you can see here, we have some correspondences here. We have a correspondence here and one here. And that was not the right word to use. The right word to use is an identity. Later in the class, we're going to go over a number of identities. We're going to learn to work with them, maybe prove some identities. But the two identities that I want you to be really aware of.
This must be the keyboard thing.
Yeah, I may have to open it now and then. Find my place. Sine of theta. You write it this way. Sine of theta minus 90 degrees. That's here, that's a over h. That's just the cosine of theta. The cosine of theta minus 90 degrees, that's over here. That's just the sine of theta. And if you look here, you can see that tangent of, I wrote this wrong both times, didn't I? 90 minus theta. Tangent of 90 degrees minus theta is 1 over the tangent of theta. So these are three identities. By an identity, I mean a statement that regardless of theta is going to be true. And we can use this to our advantage under various circumstances. We have a table of sines and cosines, but we only have up to 45 degrees. That's sufficient because between 0 and 45 degrees. Because using these identities, we can then immediately find the values for angles between 45 and 90 degrees. Okay. Questions? This is our first identity, I guess. Some books treat this as an identity. Some will treat it as a definition. It kind of depends on where you start. I wouldn't worry about the distinction. All right. I think I'll see if I can leave this up for a moment. The next thing I want to do is, it's not going to be in my notes. It's an idea I had this morning. It's definitely a trig mathematical kind of issue, but it struck me that the thinking that we're going to go through is not that different from what you might want to do as, say, a computer programmer trying to figure out how you're going to solve a certain problem. We're not going to do any coding, that's not what I mean. We're just going to look at the structure of the problem. So in particular, the problem I want to talk about is solving all possible right triangles. So what do I mean by that? Well, let me give you an example of something that I don't mean. Let's say I have a triangle. It's a right triangle. So by definition, I know one of the angles. I know that the right angle is 90 degrees. Let's say I were to know that, know just the length of one other side. Well, that triangle isn't determined. Think about it. If I know this length, this point could move up and down, these angles could change, all the other sides could change. So it's not a determined triangle. I'm interested in triangles that are determined. So clearly, just knowing one side is not adequate. Now, knowing that I have a right angle, and maybe knowing that the other two angles, that's not sufficient either. Does anybody recall why, in geometry, why that's not sufficient? Or alternatively, what do we call two triangles who have the same angles? There's a name for that. Triangle 1 is angle 1, 2, and 3. I have triangle 2. That's angle 1, 2, and 3. What are those called? They're not congruent, but you're on the right track. If they were congruent, their sides would be equal and their angles.
Is it complementary?
No, these angles are complementary. You differ by 90 degrees. Yes?
Similar triangles?
Similar triangles. Anyone remember similar triangles? Okay. Similar triangles have the same angles. Their sides are not necessarily the same, but we do know something about their sides, which is they're in the same proportion. So if I had side A, B, and C, and side capital A, capital B, capital C, we know that, say, A over B would be equal to capital A over B, A over C would be capital A over C, and B over C would be capital B over capital C. There's a few more relationships there. Okay, so that is not what I'm talking about either. These two triangles are not the same. Merely knowing three angles does not determine a triangle. So what's left? Let's think about this. So I have my right angle. If I have one angle, let's say, I'm going to change the names on these for the moment. I'm going to call these angles alpha and beta, two Greek letters. I might know alpha, and I might know, we'll just say, the adjacent side. So I have three things. That should be adequate to determine a triangle. But there are other possibilities. I might know the right triangle, the right angle, alpha, and the opposite side. And I might know the right angle, alpha, and the hypotenuse. Okay, let's keep going. I might know alpha, beta, and the adjacent side, alpha, beta, and the opposite, or alpha, beta, and the hypotenuse. Okay, that covers one angle and one side. You already saw that two angles on top of the right angle is not adequate. So there's only one other possibility, which is, I know the right angle in two sides. So what could that be? That could be the adjacent and the hypotenuse. That could be the opposite and the hypotenuse. And that could be the adjacent and the opposite. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 cases here. And I'm going to try and diagram this out because we want to go through this logically, make sure we've caught every possibility, and we want to simplify this down. So let's just start over here. I'm just going to start with each of these problems, each of these configurations, and we'll refer back to them. Okay, so some of these we can really, we can kind of coalesce pretty quickly. By that I mean, if I know the right angle, and I know one of the angles, I'm going to know the third angle right away. Right? We need a name for that process, which we, in other words, the sum of the angles is 180, so what should we call that? Just call that process capital A for angle. Okay, so we know all three angles here, so we'll have our A process. And that's going to give us, we're just going to call this, we're going to wait and see what we're going to call it. We're going to call it 1. But if I look around here, now I see case 4. Case 4, I know beta, but that's going to tell me alpha. So these two cases are now the same, right? In other words, now I know the right angle, alpha and beta, and I know the adjacent side. Okay, let's try the same thing with 2 here. We're going to use the same process, but obviously in a different case. That's going to give us, we'll call this 2. And then, which of the others are going to fall into that category? 5. Right, okay. So this is 2, 5. Right? Same thing with 3 now. Kind of doing this on the fly. Let's see how, hopefully this will look nice and clean when we're done. But okay, so 3. So you can see pretty easily that what's left is number 6. Right? So we'll call this 3, 6. Okay, so what we know about these 3 cases is we know 3 angles and one side. It's a different side in each case. Where is it? Well, wait a minute. In one case, I know the adjacent. In one case, I know the opposite. But they're really the same. In one case, it's opposite alpha, and A here is really opposite beta. So really, 1, 4 and 2, 5 are the same, right? 1, 4, 2, 5. Okay, here we know again, I'm going to say three angles and a leg, because these are legs. Here we know 3 angles and a hypotenuse. Okay, but there's a process that we can use to coalesce these. Anyone know what process I would use to get from, oh, no, I'm sorry. I'm thinking ahead. Okay, that takes care of 1 through 6 for the moment. Let's think about 7, 8, and 9. So 7, 8, and 9, we know 2 sides, but they're different sides each time. But we could kind of coalesce those too. Does anyone see some way we could kind of put these all into one category? Okay, I'll give you a hint. I'm going to call this process P. What am I calling that process P? What am I going to do there? I'm going to give you one more hint. I'm going to call it PY. Yes?
Is that Pythagorean?
I'm going to use the Pythagorean theorem. The Pythagorean theorem is going to let me take the hypotenuse and the opposite. I'm sorry, the hypotenuse and the adjacent and get the opposite. It's going to let me take the opposite and hypotenuse and get the adjacent. And going to let me take the adjacent, the opposite, and get the hypotenuse. So now we have a different case here, which is 7, 8, 9. What happened over here? Did I forget something? What did I forget? 5 and 6. 3 and 6. Alpha and beta, but we know all of them. Right, this should be 1, 2, 3, 4, 5, 6. No, I'm sorry. We're not there yet. One, 2, 4, 5. Let's look at 3, 6 for a second. We just have the hypotenuse. Oh, okay. So this may still be this is a different case. So here I have 3 angles and the hypotenuse, and here I have what do I have? Here I have 3 sides and a right angle. Okay. That really fulfills the purpose of this map here. I've taken 9 different problems, and really I only have 3 to deal with. So now we can actually get down to figuring out how to solve these. But we know we only have 3 problems to solve. So, okay. All right, let's take a look at 3 angles and a leg. So I have theta, of course, 90 minus theta, and my angle, my right angle, and one of the, I know one of the legs. It doesn't really matter. Let's just take, this one, call it L for leg. Okay, well now I want to use one of my trig functions. figure out at least, you know, the hypotenuse and this other leg. Okay, how can I do that? Well, I need some kind of relationship between them. So, for example, I call that h. That's an unknown. I can say that L over h is what? You would remember what I have for it before. This is the cosine of theta. Well, h and theta are knowns. I'm sorry, L and theta are knowns. So I can just do some quick algebra here. H will be L over the cosine of theta. So the answer to this is hypotenuse equals the leg over cosine of the adjacent angle. That gives me hypotenuse, right? What else do I need to know? I know 3 angles, I know a leg, I know a hypotenuse. What am I going to do now? I have 2 points, actually. I want to get the third side or the other leg. Nobody has any idea. If you're following me, are you following me? Okay.
You said you wanted to get the third leg. What's the question? How to get the third leg?
Yeah, I've got 3 angles. I've got a leg, and now I've got the hypotenuse. I want to get this last leg here. We'll call this L1 and L2, right? I had L1, right? I have hypotenuse, leg 1, I want L2. Yes, Ian?
Well, you could use tangent, right? But could you also use a Pythagorean?
As I said, there's a few different routes here. You could use tangent. Now let's see, how can we do that? Well, you know, L2 over L1 is the tangent of theta. And I know L1, so L2 is just L1 times the tangent of theta. Okay? That's one way I could find that. I mean, you know, one way is good enough, but how else could I find the missing leg? And there are 2 other ways you could do it. Yeah? Sine theta equals L2 over H. Okay. Yeah, so in this case, L2 equals H sine theta. That was good. Call that the sine method. And there's one more way we could find that L2, given what we know. All right. We're tired. We're hungry. We want to go home. How about Pythagorean theorem? Right? L2 is square root of h squared minus L1 squared. Okay, we don't have to use all 3 of them. We can just use one of them. But so now we've got 4 cases, and we know how to completely resolve the triangle. All right, how about 3 angles in the hypotenuse? Okay, let's kind of look at that this way. Well, I'll say L1 question mark and L2 question mark. So I have these angles. I have the hypotenuse, but I want to find L1 and L2. How can I do that? Yes?
Sorry, I just had a question about the other example. Wouldn't it be better to use tangent than sine or the Pythagorean theorem, because you're not assuming that you know what the hypotenuse is? Because in that one you have to find it, and so finding the third leg would be dependent on you having the right answer for the hypotenuse, but it wouldn't be if you used tangent.
Okay, that's it. Now you're thinking like a programmer, more than a mathematician, right? You're right. From a mathematician's point of view, well, we figured it out. We have it. We know exactly what it is. But from a programmer point of view, well, you did a calculation. Maybe there's some error. You want to keep some error out. So, you know, logically, from a mathematician's point of view, there's no difference. But there might be a difference. Maybe one of these methods is faster. Maybe you have to do this 1 billion times a second, and you're trying to save cycles on your computer. So yes, it's a good question. Is this better? In some circumstances, yeah, it would be maybe a more efficient way to do it. But again, you know, it might take more processor to find the tangent than to just do this calculation. These are questions, you know, you might want to investigate if this becomes an important problem. Okay, back to 3-6 here. We know the hypotenuse, we know 2 angles, we know the right angle. How can we find either one of the legs? This is, you know, I don't want to say it's creative thinking, but this is kind of very methodical, logical thinking. You know, it's a puzzle. We have to, you know, our input to this thing is one of these problems. A triangle where we know 3 parts. We actually, you know, we could put the other examples too. You know, 3 angles as you know, kind of black, you know, dark alleys. You know, if you get this problem, you can't solve it. You might want to know that. But these we can all solve. How do we go about it? Right? How do we go about it? You know, we use the fact that a triangle has 180 degrees. We use the Pythagorean theorem. Here we're using one of 3 things: either the Pythagorean theorem, the tangent function, or the sine function. We didn't really, I guess here I should call this process C. So we're using the cosine function. So I just want to complete this, right? I want to know, how do I get either L1 or L2, knowing everything else I know, the hypotenuse and the 3 angles? Maybe somebody who hasn't answered yet? Yes.
If you're looking for L1, could you do, what is that, cosine of theta?
Okay, cosine of theta is what? Cosine of theta is L1 over the hypotenuse. Oh, so L1 is just h times the cosine of theta. That sounds like something we might have done here. No, we sine of theta. Okay. Right, so we'll call that the cosine process again. So now we have L1, H, and L2. I'm sorry, L1, H. We don't have L2. Now we're repeating ourselves. How am I going to find L2? There's a few different ways we could do it. I just need to know one.
Is it the H equals L over?
Which L? L1 or L2?
Well, finding L would be L2 over cosine.
Cosine of, let's see, L2 over I think you're onto the right track here. Let's turn this sideways in our heads, right? And then the cosine of 90 minus theta is L2 over H. The adjacent over the hypotenuse, is that kind of what you were thinking?
Oh, okay.
Yeah, but we already know the cosine of 90 minus theta is just sine of theta. And we know H, so L2 equals sine of theta times H. Okay, so that's how we get from here to, we're done. Okay, we're just missing one kind of piece of the puzzle here. Right, let me kind of draw it this way. We know H, we know L1, we know L2, we know we have a right angle. Theta and its complement are unknowns. That's the last piece here. How are we going to figure those out? Let's call this theta question mark. Ideas? We just need to use one of our relationships here. You just pick one. Anybody want to try? I want to find this angle. I know L1, L2, and H. There's some relationship that I can connect the dots here. Yes?
Will we use cosine?
We could try. Cosine of theta question mark? What's cosine of theta question mark? You can do it. It's H. Yes. Okay. All right. Well, let's just write it that way. But now we have to, we don't know what the cosine of theta is because we don't know what theta is yet, right? We just know what L1 over H is. So how are we going to solve
what did you get, inverse?
Inverse, yeah. Yeah. We can find, this is very similar to what we were doing with exponents, exponential functions and logs. We can find the inverse function of cosine of theta on both sides. Well, this is just going to be theta, and there we have it. And we know once we have theta, we know the other angle because that's just 90 minus theta. So that's, I don't know how to really, all right, inverse cosine, how about that? And that solves it for us. Okay, maybe this wasn't the right way for you to look at it. But again, think of the problem. The problem is we have a right triangle, we know some of its parts, and we want to find the rest, if we can. So we have to go through some kind of process. Now, you won't sit down on an exam and get a problem like this and go, let's see, what's that? Where's that diagram? I mean, you could. If you're writing a computer program, you might want to diagram it out so you get each case and you code each case. But you need to think logically like this. You know, I've got this piece. How do I get this piece? What is the next step? That's what you're going to need to do. Now, when I first came up with this, I thought, oh, right triangle. That's simple, right? Apparently, it's not that simple. But we're going to come back to this idea in maybe a couple weeks. We don't have the tools yet, but I can tell you what the problem is. Now we've got a triangle. It's got 3 angles, alpha, theta, gamma. It's got 3 sides, A, B, C. And what are the possibilities? What are the possibilities? Well, we already know just knowing 3 angles is not sufficient. Okay. But we know that if you know 3 sides, that determines a triangle. So if we have the 3 sides, we ought to be able to determine the angles somehow. We need a little more trigonometry. We need a little more equipment here to do that. Really, you can just kind of list off those geometry theorems that we talked about. There was side, 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 angle, side, angle. Really what we covered today, well, it's mostly HL, because we're dealing with a right triangle. But we're going to learn enough new stuff. We're going to have enough new equipment or machinery that we will be able to solve every solvable triangle. There may be circumstances where we can't. We'll find out about that. All right. Just let me know if this gets in the way. All right. We're going to start talking about some background. We're going to talk a little bit about angle measure. You may recall that from geometry that we define an angle in terms of two rays. We have a vertex and two rays. And we call this entity that we create between them an angle. And we can also talk about the measure of this angle. So historically, we talk about degrees, and we think about a complete circle having how many degrees? 360? 360 degrees. This is a somewhat arbitrary number, not entirely arbitrary. I believe it goes back to the Phoenicians. They had a kind of a base 60 number system. You see a lot of that still today. How many minutes in an hour? How many seconds in a minute? Anything else that we use 60 for? And degrees. This is actually, just a side note, this is actually a nice number for a certain reason. It's evenly divisible by 2, 3, 4, 5, yes, 6, not 7, not 8. I guess that's really it, not 9, but at 10, right? And of course, 12, 15, 30. So, you know, before you enjoyed the joys of placement, right? This is not a bad numbering system to use, and that's why this is 360. Which is 6 times 60. This is not the only scale that you might run into. There's another scale called a grad, in which a circle has 400 degrees. This is sometimes used in navigation, but you're unlikely to run into it. Really where this comes from is the idea you make what we call a 90-degree angle 100 degrees, and it's more of a decimal kind of a system. But I bring this up because we're going to look at a different scale, which in some sense is more of a natural scale. Again, we're gonna look at an angle, and we're gonna add some definitions here. We're going to call one of the rays the initial side of the angle, and the other the terminal. And we're going to do something a little different to measure the angle. We're going to take a circle of radius 1 and put the vertex at the center of that circle. And we're going to measure the length of this arc here. And we're going to give the measure of this angle here, this theta. We're going to say theta is equal to s, that length. Drew the We're going to call this radian measure. As I said, it's sort of a more natural scale. That won't seem apparent right away because it's not really clear what a radian is. We have some idea what a degree is. We know 90 degrees, but a radian's a little different. There's an alternate way you can think of a radian. You can just draw some arbitrary circle, arbitrary radius r, and you know what to call this? Let's call this capital S. And then our radian measure is capital S divided by the radius. This can be useful in another form if we happen to have a circle and we know its radius, and we have the radian measure. We can rewrite this r theta equals s. So again, if we have the radian measure, radius, we can tell what the length of that arc is. Right. So if the circle is, well, it's 180 degrees, it's 360 degrees, what's the distance around a circle in radians? Well, using the alternate definition, right, if you have a radius and circumference of a circle, well, what's the circumference of a circle divided by its radius? Well, we know that the circumference of a circle divided by its diameter is what? That's a number we know. Yeah?
360 over 2.
I'm just talking about the lengths now. The circumference, the length of the circumference of a circle divided by its diameter. Maybe it would help if I said the diameter times x equals the circumference. What's that number? Yes?
Is it pi?
That's pi. Yeah. C over d equals pi. But that's just c over 2r is pi. So c over r will be 2 pi. That is to say, the radian measure around a circle is 2 pi. Right? So I think we need a little chart here. Degrees and radians. So 360 degrees is 2 pi radians. What about a right angle? That's what? 90 degrees. So what will that be? Yes? Pi over 2. You know, if you recall, there's something called a straight angle. Kind of a straight line. That's 180 degrees. What would that be? Pi. Okay. These these are really good numbers to know. There are a few other conversions. Very important, 60 degrees. 60 degrees, that's 1/6 of 360. So 1/6 of 2 pi is pi over 3. And the last one that's pretty useful is 45 degrees. That's half of a right angle.
Pi over 4.
Pi over 4. Even though this is a hard number to write out, any of these numbers will apply, these are exact conversions. Right. There's one last thing I'd like to do with radian measure today. We're not even remotely done with it, but let's start with something I think everybody's familiar with. I have a circle of radius r, and I want to know its area. Paul, you know the radius area of a circle, don't you?
Is it a pi r squared?
It's pi r squared. Okay. What if I wanted to take a piece of the circle, a sector, and I wanted to know its area? So we'll call this theta. We want to know the area of theta. Well, the area of theta is going to be to the area of the whole circle. Let's call that area of theta relative to the whole circle is going to be in the ratio of theta to what? What's the whole angular measure of the circle? Pi. This is theta in radian measure now, right? Okay. This is what I want to know, so let's solve for it. Area of the theta sector, that's going to be the area of the circle times theta over 2 pi. But let's plug in the area of the circle here. Pi r squared times theta over 2 pi. Well, we can reduce that. The pi drops out. What do we have? We have the area of this sector is theta r squared over 2. So now, if I have the radian measure of some angle and the radius, I can find the area of the sector. All right, let's just do one simple example. I have a circle. Its radius is 3 meters. And I want to know the area of a sector which is 60 degrees. Well, first thing I want to do, I want to convert my 60 degrees over to radian measure, so that's just pi over 3. And then I can just use my formula. It's going to be pi over 3 times the radius squared, that's 9 over 2. So that'll be 3/2 pi. Is that right? Yeah. think that's enough for today. Again, I'll be in my office. I'll try and be there 2 to 4. Have questions,